Welcome to another lecture to this course of computer aided power system analysis. Till the last lecture, we have discussed about the neutron Raphson load flow both in polar coordinate as well as in the rectangular coordinate. We have seen that both in polar coordinate as well as in the rectangular coordinate, all the equations are coupled with each other. Now, what do we mean by this statement? So, let us look at that. So, in the polar coordinate, for example, NRLF polar, the equations we have is J1, J2, J3, J4 and then delta theta, delta V. Please note that this J1, J2, J4 all are matrices of appropriate dimensions. Then we have delta P, delta Q vector. So, then if we do expand this, what equations I get? I get J1 into delta theta plus J2 into delta V is equal to delta P, and we get J3 into delta theta plus J4 into delta V is equal to delta Q. So, if we solve them, what we get? We would be able to solve for theta and V, but then what you can see is that both theta and V, they are actually dependent on both P and Q, which is obviously the case. But then for all practical purpose, we can show, which we will actually show, that with some simplifying assumptions, it can be shown that the variation of theta is largely dependent on the variation of P, that is the real power, while the variation of voltage magnitude, that is this vector delta V, is largely dependent on the variation of Q, that is the reactive power. In other words, the variation of theta is not dependent on Q, while the variation of V is not dependent on P. So, it will actually help us to expedite the solution. Now, to do that, we have some simplifying assumptions. So, we have some simplifying assumptions. So, let us look at those simplifying assumptions, under which assumptions this is true. And so, first look at these simplifying assumptions. So, first assumption is all voltage magnitudes are nearly equal to 1.0 per unit, that is, we should say that all Vi is roughly 1.0 per unit, which is almost true, because we have already seen in our example that for this 5 bus system, for example, we have seen that all these voltage magnitudes are more or less equal to 1.0 per unit, that is, they are very close to 1.0 per unit. We may ask the questions that is it a kind of general situation? To some extent it is, because in any power system you would like to maintain the voltage magnitudes at all the buses equal to their nominal voltage. Nominal voltage means nothing but this rated voltage, which in turn in per unit is nothing but equal to 1.0 per unit. So, then therefore, because we wish to maintain the voltage profile of any power system network at the rated voltage, so then therefore, we can say that all the voltage magnitudes are more or less equal to 1.0 per unit. Second simplifying assumption is for all transmission line, for all transmission line Gij is very less than is Bij. What is Gij and Bij? Gij and Bij are nothing but the conductance and the susceptance. That is, if we take the inverse of the impedance, that is Y. So, that is, if we compute Y, that is the line admittance, that is 1 by Z. So, that is equal to actually Gij plus J Bij. Now, what is the justification of this? Now, we have that J is equal to R plus Jx, where R is the resistance and X is the inductance. And in a transmission system, usually the resistive part is much less than reactive part. So, then therefore, we know that R is much less than X, usually R is much less than X. Now, Y is 1 by R plus Jx. So, we have got R minus Jx by R square plus X square. So, it is R by R square plus X square minus Jx by R square plus X square. So, then therefore, we can write down that Gij is equal to R by R square plus X square, or rather this magnitude of Gij, and Bij is minus X by R square plus X square. As R is very less than X, so then therefore, Gij would be very less than Bij, because this denominator is same for both Gij and Bij, and as R is very less than X, so then therefore, Gij would also be much less than Bij. So, this is the second assumption. Third assumption is, for any transmission line between bus I and J, the angular difference between them, theta I minus theta j, is quite small. So, we say that it is roughly 5 to 10 degree. We say that is, in our parlance, we say that is approximately equal to 0. Now, what is the justification for this? We know from our equal area criteria that for maintaining stability, the angular difference between two terminals of a line must be as small as possible, because if the angular difference of the voltages between the two terminals of a line is increased, so then therefore, the possibility of instability for any fault in that line increases severely. So, then therefore, for maintaining the stability of the system, we need to maintain the angular difference between the two terminal voltages as low as possible. So, then therefore, according to that, so we take that assumption and we say that for any transmission line between bus I and j, the angular difference of the voltages between two terminals are approximately equal to 0. Approximately, it is not equal to 0, it is approximately equal to 0. And the fourth one is in per unit Qi, that is the injected reactive power at bus I, is much less than Bii into Vi square. Now, what is the justification for this? Please note that it is in per unit. So, Qi is much less than as compared to Bii into Vi squared. Now, what is the justification for this? The justification is that in per unit, for example, at any bus, let us say the reactive power load is 50 MVAr, 50 MVAr. At a bus, the reactive power load is 50 MVAr. Let us say our base MVA AS is 100 MVA. So, then therefore, in per unit, so then in per unit Qi, that is magnitude, is equal to 0.5. So, this is basically the numerical value 0.5 in per unit. Now, we know that Bii is nothing but the sum total of all Bij, where j belongs to the set omega, where omega is the set of lines directly connected to bus I, right. So, then therefore, j is actually basically, or rather we should say that omega is the set of the indices of the lines of is the set of indices of the line indices of lines directly connected to bus I. For example, just to give an example, suppose I do have bus, let us say bus 3 at some bus in some system, and let us say this bus 3 is directly connected to bus 4, and let us say this is bus 7, and here it is connected to, let us say, bus 13. So, then therefore, in this case I is 3 and set omega would be 4, 7 and 13, and j is omega, and j belongs to omega. So, then therefore, here in this case this j would be 4, 7 and 13, and then therefore, this Bii, which is nothing but the imaginary part of the diagonal element corresponding to bus I, that would be nothing but, we know from the basic formulation of the Y bus matrix that this any diagonal element is nothing but the sum total of all the admittances of the lines directly connected to bus I. So, then therefore, the imaginary part of the admittance corresponding to the diagonal element would also be nothing but the sum total of the imaginary part of the admittance of all the lines directly connected to bus I. So, then therefore, now from this, now if we look at this expression, Bij, if I just look at this expression Bij, r square is quite less in per unit. Please note that all these calculations are being done in per unit. So, then therefore, r is a value which is small in per unit, let us say 0.03 or let us say 0.0023, something like that. X is also a value which is also pretty less. So, then therefore, r square would be even reduced, x square would be even reduced. So, then therefore, r square plus x square would be a very small quantity, and x, although it is a small quantity, but because this is squared. So, then therefore, this divided by this would be actually a very large quantity. Now, because this Bij in numerical value would be a large quantity. So, then therefore, in numerical value numerically Bii would be also a very large quantity, and even though if we do assume that this Vi is almost equal to 1.0 per unit. So, even then, even if we take that this Vi is equal to 1, So, even then, because BII numerically is very large value, so then therefore, numerically BII into VI square would be pretty large as compared to QI in per unit because of this numerical value. So, with these 4 assumptions, now if we apply these 4 assumptions to our equations of Newton-Raphson polar coordinate, some very interesting results can be obtained. So, let us look at that. So, we will apply these 4 simplifying assumptions one by one, and we will see that what conclusion we draw. So, again we write, this is again we discuss about NRLF polar, and we again just it is recollection. So, delta theta, delta V, delta P, delta Q. Now, what is J1? J1 we know that it is del P by del theta. We have already defined what is mean by del P by del theta. J2 is del P by del V. J3 is del Q by del theta, and J4 is del Q by del V. So, first let us look at this 2 off diagonal submatrices. If we think of this particular big matrix J constituting of 4 components J1, J2, J3, J4. So, first let us look at J2 and J3. So, J2 is del P by del V. So, we have got, as we have seen, so we have got 2 general expressions. One is del Pi by del Vi, and another is del Pi by del Vj, j not equal to I. So, these are the 2 expressions we have. We have Pi is equal to, we know that Vi, Vj, Yij cosine of theta I minus theta j minus alpha ij. J is equal to 1 to n, n is the number of bus. So, it is, we know that it is Vi square Gii, we have already done it, we are just merely recapitulating it. J is equal to 1 not equal to I, goes up to n, Vi, Vj, Yij cosine theta I minus theta j minus alpha ij. So, this is the expression. So, now again let us do this too, and then we apply these 4 assumptions one by one judiciously. So, let us start. So, first we look at the simpler one. So, we del Pi by del Vj with the condition that j is not equal to I. So, what it would be? So, it would be basically we have already seen. So, this will go and there will be only one term of Vj. So, it would be Vi Yij. So, it would be Vi Yij cos theta I minus theta j alpha ij. So, now we Vi Yij, so this is cos A cos B cos theta I minus theta j cos b cos a minus b. So, cos a cos b plus sin a sin b sin theta I minus theta j sin alpha I j. Now, you know that y I j into cos alpha I j is nothing but g I j. So, we write V I g I j cos theta I minus theta j, and we know that y I j into sin alpha I j is b I j. So, we write b I j sin theta I minus theta j. So, this is the expression. Now, we apply this simplifying assumptions. The simplifying assumption is we apply two assumptions. One is that g I j is much less than b I j, and another assumption is theta I minus theta j is approximately equal to 0. These two assumptions we apply. Now, if we do apply these assumptions, so what we get? Sin theta I minus theta j, because theta I minus theta j is approximately equal to 0. So, then therefore, sin theta I minus theta j is also equal to approximately equal to 0. So, this is 0, this part, and because g I j is much less than b I j, we can say that this part g I j is also approximately equal to 0. But remember, because theta I minus theta j is approximately equal to 0. So, cos theta I minus cos theta j would be approximately equal to 1, but because g I j is very small, so we can neglect it as compared to b I j. So, then therefore, for all practical purpose we take g I j to be equal to 0. So, this part becomes approximately equal to 0, and because of this assumption that theta I minus theta j is approximately equal to 0. So, then therefore, sin theta I minus theta j also becomes equal to 0. So, then therefore, this term becomes equal to 0, this term becomes equal to 0. So, then approximately del pi by del V j, where j is not equal to I, becomes equal to 0. So, this is a very interesting result. So, we get this result. So, this is the first result. Now, look at this one. So, it would be 2 V I g I I plus j is equal to 1 to n not equal to I. It would be V j y I j cos theta I minus theta j minus alpha I j. Because we are taking the derivative with respect to V I, and from this expression V I would be everywhere. So, then this summation term will come. We have already looked into this. So, now if we expand this part as we have done here, so we can write straight away without any problem, this is 2 V I g I I plus j is equal to 1 not equal to I equal to n V j then g I j cos theta I minus theta j plus b I j sin theta I minus theta j. So, this part is identical of this. So, we have just taken this result as it is. So, as usual as before, what we get, as before we get that this is almost equal to 0, this part is almost equal to 0, and GII, because all GIJ is much less than BIJ. So, then therefore, GII would, and so then therefore, GII, which is nothing but the sum total of all GIJ, we again repeat, we write that, we again note that GIJ, we write it here, just GIJ is sum total of GIJ, where J belongs to the set omega. So, then therefore, because all GIJs are very very negligible, so then therefore, their sum total would also be very very small. So, then therefore, GII would also be very very small. So, then for all practical purpose, GII would also be 0. So, then therefore, del Pi by del Vi would also be 0. So, then therefore, what we get is, we get del Pi by del Vi is also equal to 0. So, then for this matrix J2, we have terms del Pi by del Vi, which is 0, and del Pi by del Vj, that is equal to 0. So, then therefore, we can straight away say that J2 matrix is a null matrix. So, this is a very very interesting result. So, matrix J2 becomes a null matrix, it becomes simply a null matrix. Now, let us look at this matrix J3. So, we have matrix J3, that is basically del q by del theta. So, we know that it has got two del qi by del theta j. So, one is j is equal to I, and another is del qi by del theta j, j is not equal to I. We all know that how qi varies and how j varies. For example, I would be varying from m plus 1 to n, and j would be varying from 2 to n, and etcetera, all these are known. So, this is it. So, then we have this two terms. So, then therefore, when I varies from m plus 1 to n and j varies from 2 to n, so then therefore, there will be some occasion where j would be equal to I, and also there would be some occasion and in basically most of the occasions j would be not equal to I. So, then we again need to look at these two expressions as we have looked into J2, and then deduce what happens to this matrix J3. So, this we will look into this next lecture and also along with the other lectures. Thank you.